Okay, in this video we're going to be looking at comparison test. We'll be looking at first the direct comparison test and then secondly the limit comparison test. The direct comparison test is a little bit more difficult to use because of how you need to show the relation of one sequence is smaller than another term by term or larger. And the limit comparison test is a little bit easier to use. We'll also be comparing these to, so with the comparison test you're going to compare typically to a p-series or a geometric series. Those are typically the types of series we're going to do a comparison with, and these tests will tell you convergence or divergence only. So let's look at the direct comparison test. And it says, suppose that there exists an integer n such that 0 is less than or equal to a sub n, which is less than or equal to b sub n for all n greater than or equal to sum n. If the sum n equals 1 to infinity of b sub n converges, then so also does the sum n equals 1 to infinity of a sub n also converges. So if we look at the partial sum of s sub a sub n minus 1, which would be a sub 1 plus a sub 2 all the way out to a sub n minus 1, and that's going to be less than or equal to s of a sub n minus 1, so the same thing, plus the sum n equals n, so lowercase n equals the uppercase n, up to sum n of a sub n. And we're going to know that by our assumption that once we get past n, then the b sub n terms are going to be larger term by term. So this is going to be less than or equal to s of a sub n minus 1 plus the sum n equals big N to m of b sub n. And this is going to be less than or equal to s of a sub n minus 1 plus, and we could say that the full series sum is going to be greater than just a partial sum, so the sum n equals 1 to infinity of b sub n will be larger than the partial sum from n equals uppercase n to m, and which we're going to say converges to L. So we have this is equal to s of a sub n minus 1 plus L. And so we have the partial sum bounded by a finite number, s of a sub n minus 1 plus L, and we can do this for as far as we want in terms of letting the m go to infinity, and so this will force the a sub n to converge. Now on the other hand, let's say that this diverges and we have this relation, then this is going to be forced to infinity as well. And that's the second condition here. So suppose that there exists an integer n such that a sub n is greater than or equal to b sub n, which is greater than or equal to 0 for all n greater than or equal to n. So then if b sub n is divergent, so then will also the a sub n. So here we would be making the replacement of b sub n here and a sub n here. So b sub n would be the smaller series that diverges, forcing the larger series to diverge. So let's go ahead and look at some examples to see how this works out. Okay, all right. So we're going to look at the sum n equals 1 to infinity of 2 over n plus 1. And so this is kind of like the harmonic series 1 over n. So we're going to compare it with the harmonic series 1 over n. Sum equals 1 to infinity of 1 over n. And this is a divergent p-series with the p equals to 1, and that's less than or equal to 1. So if your p was less than or equal to 1, then your p-series diverged. So what we want to do is we want to show that 1 over n is smaller than 2 over n plus 1. And so if we can show that the smaller series diverges, then so will the larger one. So we want 1 over n to be less than or equal to 2 over n plus 1, and we just want to see if we can manipulate this and get a true statement. So you can go ahead and cross multiply. That's going to be preserve the inequality, so n plus 1 is less than or equal to 2n. You can subtract n from both sides, and 1 is less than or equal to n, and that's true for all natural numbers. And so 1 over n is less than or equal to 2 over n plus 1 for all n. And so that's good enough for the direct comparison test. That's what we need. So this is a true statement. Since 0 is less than 1 over n, which is less than or equal to 2 over n plus 1, for all n greater than or equal to 1, and the sum n equals 1 to infinity of 1 over n is a divergent p-series, the sum n equals 1 to infinity of 2 over n plus 1 diverges by the direct comparison test. Okay, so let's go ahead and look at another couple examples here. So let's go on to example number 2. We'll look at the sum n equals 1 to infinity of 2 over 4n squared plus 1. And so this is a little bit like the infinite series n equals 1 to infinity of 1 over n squared. So this is going to be another p-series. And this time it's going to be a convergent p-series, the sum n equals 1 to infinity 1 over n squared. And this is a convergent p-series. Your p is equal to 2, and that's greater than 1. And so if your p was greater than 1, then we had a convergent p-series. Now if we want to show convergence, we want what we're comparing it to be larger term by term. So we want the 2 over 4n squared plus 1. We would like that to be less than or equal to 1 over n squared. And so this is not always easy to show, and so using the direct comparison test can be difficult. Sometimes you might want to use limit comparison test instead. Alright, so we're going to go ahead and cross multiply. The inequality will be preserved. And we can subtract 2n squared from both sides. And so 0 is less than or equal to 2n squared plus 1. And that's going to be true for any positive integers. So we only really need this for n greater than or equal to 1. So we have that condition met. And so since 2 over 4n squared plus 1 is less than or equal to 1 over n squared, and certainly the 2 over 4n squared plus 1 is greater than or equal to 0 for all n greater than or equal to 1, and the sum n equals 1 to infinity of 1 over n squared is a convergent p-series, the sum n equals 1 to infinity of 2 over 4n squared plus 1 is going to converge by the direct comparison test. And we're directly comparing it to the convergent p-series where p is equal to 2. So again, when you're doing the comparison test, you're typically going to compare to a p-series or a geometric series. And so in the next example, I think we're going to be looking at a geometric series. So we're going to look at the sum n equals 1 to infinity of 2 to the n over 3 to the n plus 1. Okay, and we're looking at the 2 to the n over 3 to the n, which is the same as 2/3 to the n. So we're going to compare it with the convergent geometric series. Sum n equals 1 to infinity of 2/3 to the n. Your common ratio in absolute value is 2/3, and that's less than 1, and so that's when we have convergence with the geometric series test. So if we want to show convergence with the comparison test, we need to show that what we're comparing to is larger. So what we want is the 2 to the n over 3 to the n plus 1 to be less than or equal to 2/3 to the n, which is the same as 2 to the n over 3 to the n. You can cross multiply. So you have 2 to the n times 3 to the n, less than or equal to 2 to the n times the quantity 3 to the n plus 1. At this point in time, we can go ahead and divide by 2 to the n, and so we'll have 3 to the n is less than or equal to 3 to the n plus 1. That might be convincing enough, or we can subtract 3 to the n from both sides. So 0 is certainly greater than or equal, less than or equal to 1 for all n greater than or equal to 1. So that's true. So we have the conditions of the comparison test met, and so we can go ahead and make our conclusion. And so since 2 to the n over 3 to the n plus 1 is less than or equal to 2 to the n over 3 to the n, for all n greater than or equal to 1, and the sum, n equals 1 to infinity, of 2/3 to the n is a convergent geometric series, because the fact it's convergent, the other series that we're comparing it with is also going to converge. So the sum n equals 1 to infinity of 2 to the n over 3 to the n plus 1 also converges, and this is by the direct comparison test. Okay. So that is the direct comparison test. Now we're going to take a look at the limit comparison test. If I were given the choice of using the comparison test, I would always want to use the limit comparison test because it's typically easier to use. So the limit comparison test says that if a sub n and b sub n are greater than or equal to 0 for all n greater than or equal to 1, and of course we want to make sure that the b sub n is not 0. And so we'll look at three different things. If the limit as n goes to infinity of a sub n over b sub n is equal to L, and that's not equal to 0, then both the sum n equals 1 to infinity of a sub n and b sub n will both converge or both diverge. So what you're going to do is you're going to compare to either a geometric or p series that you know converges or diverges. If the limit as n goes to infinity of a sub n over b sub n is equal to 0, and we know that the sum n equals 1 to infinity of b sub n converges, then so will the sum of the a sub n converge. If the limit as n goes to infinity of a sub n over b sub n is equal to infinity, and the series n equals 1 to infinity of b sub n diverges, then so will the series. That looks like it's a typo. Let's go ahead and fix that. And that last one, let me fix the typo there. It says, if the limit as n goes to infinity of a sub n over b sub n is equal to infinity, and the sum n equals 1 to infinity of b sub n diverges, then so will the sum n equals 1 to a sub n. The sum n equals 1 to infinity of a sub n, that will also diverge. So to kind of get an idea of how it works, we're going to suppose that the limit as n goes to infinity of a sub n over b sub n is equal to L. Okay, and L is not equal to 0. So if we look at maybe saying epsilon is equal to 1, then there exists a natural number n such that for all n greater than or equal to n, so for all lowercase n greater than or equal to uppercase n, 0 is less than a sub n over b sub n, which is less than L plus epsilon, or L plus 1, which is your epsilon. So we can go ahead and rewrite this and say, so 0 is less than a sub n, which is less than b sub n times L plus 1. Okay, for all n greater than or equal to n. Since the sum n equals 1 to infinity of b sub n times L plus 1 is going to converge, so we'll make the assumption that the b sub n series converges, then if we multiply it by a constant, that's not going to affect it converging. So because that series converges, this implies that the sum n equals 1 to infinity of a sub n converges, and that's using the direct comparison test. Okay, and this, if the sum of a sub n diverges, okay, since it's smaller than the b sub n, then the b sub n will also be forced to diverge there. Okay, so we're going to look at two examples here, and then we'll have one or two more examples on the following videos. So let's go ahead and jump in and do an example or two. So let's look at the sum n equals 1 to infinity of 3 divided by 7 to the n plus 2. This looks like a geometric series. The only thing that has the power of n is 7, so we're probably going to compare it to a geometric series of common ratio 1/7. So we're going to compare with a convergent geometric series. N equals 1 to infinity of 1/7 to the n, common ratio in absolute value is 1/7, which is less than 1, and that's the condition for a convergent geometric series. Okay, so we're going to look at the limit as n goes to infinity of 3 over 7n plus 2 divided by 1 over 7 to the nth power. Okay, all right, and then we're going to go ahead and flip over the dividing fraction, so we have 3 times 7 to the n over 7 to the n plus 2. This is going to be an infinity over infinity. You can do it with L'Hopital's rule. You can factor out a 7 to the n. You got some options here of figuring out what this limit is. So it's going to be the limit as n goes to infinity of 3 times 7 to the n, natural log of 7, so we're applying L'Hopital's rule, divided by 7 to the n, natural log of 7, which is going to simplify down to just 3. And so that limit is a constant. It's not 0. And so the limit comparison test said as long as that limit wasn't 0, they are both going to do the same thing. Since we know that we have a convergent geometric series, the series that we're comparing with is also going to converge. So since the sum n equals 1 to infinity of 1/7 to the n is a convergent geometric series, the sum n equals 1 to infinity of 3 over 7 to the n plus 2 converges by the limit comparison test. Okay, so we got one more to look at in this video, and then we'll be off to the next one. All right, so we're going to look at the sum n equals 1 to infinity of 1 over n squared times n plus 3. Okay, so your options are geometric series and p-series. This looks more like a p-series. The degree of the denominator is 3. The degree of the numerator is 0. So you want to compare it with a degree 3 p-series. So we're going to compare with a convergent p-series with the p equal to 3, which is less than, sorry, it's not less than, greater than 1, so that's our condition for convergent p-series. So the sum n equals 1 to infinity of 1 over n cubed is a convergent p-series. Now we're going to do the limit comparison test. So the limit as n goes to infinity of 1 over, and I'm going to go ahead and distribute the n squared, so that would be 1 over n cubed plus 3n squared, and then divided by 1 over n cubed. And we're going to go ahead and flip over the dividing fraction, and that will become n cubed over n cubed plus 3n squared, and we're taking the limit. So this is going to be an indeterminate form, infinity over infinity, so we can either factor out n cubed, or we can use L'Hopital's rule a couple of times. So it is going to be a limit of 1, that's your horizontal asymptote. That's not 0, and so both these series are going to do the same thing. Since the sum n equals 1 to infinity of 1 over n cubed converges, so will the series we're comparing it to. Okay, all right. Since the sum n equals 1 to infinity of 1 over n cubed is a convergent p-series, the sum n equals 1 to infinity of 1 over n squared times n plus 3 converges by the limit comparison test. All right, and so we're getting more and more tests here. We've had the geometric series test, the p-series test, telescoping series test, the nth term test for divergence, the direct comparison test, the limit comparison test. I think that's, oh, and can't forget the integral test. We got the integral test. In section 5.5, we'll get the alternating series test, and in section 5.6, we'll get our last two, the ratio test and the root test. So we're getting a lot of tests here. We have 10 different tests, a lot of knowing which series test to use. Some of that comes from experience, identifying what kind of series we're looking at, what test applies, and what does that test tell you. So So you just got to get in there and practice, and there's some good tables in your textbook to kind of help you out with that kind of thing. All right, stick tuned to the next video, and we'll have a couple more examples. So we'll see you next time.